So, can you see my PPT slide? Hello?
Yes, sir.
Yes, sir.
Okay. So, I will continue on our yesterday discussion. So, yesterday we already discussed about the internal force. Okay, slightly discussed about internal force, but previously we already discussed about the distributed force, right? And for today, we will concentrate more on the internal force. Okay, what is internal force? So basically, if you have some kind of stone or egg like that, okay, I think it's better representation if we talk about stone. Okay, if you have a stone and there are several external forces, F1, F2, F3, working on the surface of the stone as external force, okay, and then we have a gravitational force as well, F, okay. What we are talking about here in this particular free body diagram is external force, okay. That's the thing that we learned up until now, okay. When we discuss about thrust, when we discuss about moving the force, the equilibrium and the force system and the resultant, okay, what we learned up until now, most of it concentrated on the external force, okay. We learn about the force system, we learn about the resultant force and moment, we learn about the thrust, we learn about the frame and machine, okay. Those things, those forces who works on those, okay, are external forces, okay. We haven't touched yet about what is happening internally on the structure, yeah. We haven't touched it yet. We haven't touched it yet on what is happening inside of the structure, okay. Because when we talk about failure in the structure, okay, the one that determines the most is not the external force, but the value of the internal force and moment, okay. Because those internal force and moment is the one that we will convert it into stress, okay, and that value is the one that will cause failure in the structure. So internal force, in order to determine whether a structure will fail or not, okay, we have to know the stress inside of the structure, and in order to do that, we have to know about the internal force inside of the structure first, okay. So that's it. It is very important for us to understand about internal force. And internal moment, of course. Okay, internal force and internal moment. Okay, and if we take a look at this particular system, okay, if we take a look at this particular free body diagram, okay, how to get internal force is actually very simple. Okay, for example, I want to get internal force at this particular point, for example, okay, at this particular location. In order to do that, what you have to do is just to do a section at that particular location. Okay, after you do the section, then okay, we have two free body diagram right now. Okay, the left section and the right section. Okay, if we take a look at the left section, this will be our free body diagram. And if we take a look at the right section, this will be our free body diagram. And both actually have internal force. Although here, the one that we draw with the internal force and internal moment is only the left one, but internal force is the same as the joint like that. The force which is happening to that particular section on the left and on the right is supposed to be action and reaction. Okay, so basically, if it, I will redraw again. If we have this, I think I will do it by myself. Okay, we can separate it into two. Okay, the left one and the right one. For example, this one is the left one, and this one is the right one. Okay, the external force is still happening there. F1, F3, F2. Okay, so the left section and the right section, the external force is still happening there. But after you do this, you do that section, okay, at the section part right now, we have to do something in order to ensure that the left, this one, the left free body diagram is in equilibrium condition. Okay. What we normally do is we add the internal force there. Okay, the internal force that we can add is the normal force. Okay, and beside that, the shear force and moment. Okay, on the right free body diagram is the same. In order to ensure the equilibrium condition, we have to add the internal force. Okay, for this one, as usual, we have shear force, normal force, and moment as well. Okay, but as I told you, okay, the internal moment, internal shear force, internal normal force, it's supposed to be action and reaction for both sides, this side and this side. Okay, because when you join both together, when you join the left section and the right section together, this is what we will get. The original free body diagram without internal force. So when you join it together, the internal force must must be action and reaction and must be zero each other when you join it together. Oke, saya coba ulangi dalam bahasa Indonesia ya. Jadi kalau misalkan kita melihat suatu struktur ya, kita melihat suatu struktur, misalkan bisa dilihat ini ada suatu batu ya. Ini ada suatu batu dengan external force seperti yang ditunjukkan pada gambar ya, seperti ini. Ini external force-nya ada F1, F2, F3, dan juga F kecil. F kecil itu adalah beratnya ya. Oke, itu adalah gaya-gaya luar ya, gaya-gaya luar yang bekerja pada batu tersebut. Nah, kalau misalkan saya ingin mencari tahu nilai dari gaya dalam yang terjadi pada titik yang saya barusan ketikkan ini ya, caranya bagaimana? Gampang, kita bisa melakukan section, kita potong di bagian tersebut. Kita potong di bagian tersebut. Nah, setelah kita potong, kita bisa mendapatkan dua sisi ya, sisi kiri dan sisi kanan. Oke, kalau kita lihat yang sisi kiri, itu F1 dan F kecil itu muncul sebagai gaya luar, tetapi karena bagian kanannya hilang, oke, kita harus menyimbangkan, kita harus memastikan bahwa equilibrium itu tetap terjaga, ya, dengan menambahkan sesuatu pada sisi apa namanya, sisi potongan kita. Nah, yang ditambahkan apa? Yang ditambahkan adalah internal force. Internal force tujuannya supaya setelah kita potong, si apa namanya, si bagian potongan tadi itu equilibriumnya tetap terjaga. Walaupun sebenarnya potongan yang kita lakukan itu imaginary ya, potongan imaginary, potongan yang tidak benar-benar kalian potong gitu ya, tetapi lebih ke arah di imajinasi kalian itu kalian coba potong, kalian coba lihat internal force yang terjadi di dalamnya seperti apa. Seperti itu. Nah, kalau kita lihat internal force yang terjadi di dalamnya seperti apa, itu caranya gampang. Kita tinggal cari nilai dari V, N, dan M, gaya normal, gaya geser, dan juga momen dalam, ya, yang menghasilkan equilibrium itu, yang membuat equilibrium tetap terjaga untuk free body diagram yang kiri, seperti itu. Hal yang sama juga hal yang sama harus dilakukan di yang kanan. Oke, ada external force F2 dan juga F3. Oke, tetapi karena bagian kirinya hilang, equilibriumnya tidak terjaga. Nah, di bagian potongan itu suka tidak suka harus kita tambahkan dengan internal force supaya equilibrium tetap terjaga. Nah, bagaimana untuk menjamin supaya equilibrium tetap terjaga? Ya, internal force dan juga internal moment yang ada di sana dibuat sedemikian rupa supaya memenuhi persyaratan equilibrium. Oke, jadi untuk bagian potongan yang kiri dia harus memenuhi sigma fx1 sama dengan 0, sigma fx2 sigma fy1 sama dengan 0, dan juga sigma momen 1 sama dengan 0. Untuk yang kanan itu harus memenuhi sigma fx2 sama dengan 0, sigma fy2 sama dengan 0, dan sigma momen 2 sama dengan 0. Nah, dengan melakukan ini, dari tiga persamaan tersebut kita bisa mendapatkan ketiga internal force-nya. Dari ketiga persamaan ini kita bisa mendapatkan tiga internal force-nya. Jadi sebenarnya kalian hanya cukup menyelesaikan salah satu potongan saja, tidak perlu dua-duanya. Oke, kalau ingin mencoba dua-duanya itu lebih ke arah untuk mengkonfirmasi hasilnya, karena hasilnya harus sama persis. Ya, hasilnya harus sama persis, tetapi perbedaannya di sana yang antara kiri dan kanan itu lebih ke arah aksi reaksi. Ya, nilainya akan sama persis, tapi arahnya akan berlawanan. Kenapa seperti itu? Karena saat kita gabungkan kiri dan kanan, hasil penjumlahannya itu harusnya seperti yang free body diagram yang ada di sini. Oke, free body diagram yang ada di situ. Oke, bagian karena kita sudah sambungkan, gaya dalamnya itu hilang, saling menghilangkan. Oke. Sampai di sini, apakah ada pertanyaan terkait dengan internal force? Yang saya lakukan di sini adalah menjelaskan konsep dasar dari internal force tersebut. Oke, silahkan jika ada pertanyaan. Oke, is there any question? No? Okay, I think I will continue a little bit. I'm sorry, this one is still in bahasa. Okay, when we talk about internal force, there are 4 types of internal force. Okay, when we talk about it, there is a normal internal force, like this, shear force, like this, moment bending, like this, and torsion, like this. It depends on the problem. Okay, but when we talk about the bending beam under bending, normally the one that we have to deal with is only these 3: normal, shear, and bending. Sometimes, most of the time, even we just need to deal with this shear force and bending moment. Okay, but that one is for beam under bending. Sometimes we have a bar or beam, bar under torsion. So we have to deal with this kind of internal moment. Okay, and some other time we have to deal with a bar under normal force. This one is normally, it's most of the time happening at the two force member. It's under normal force, either tension or compression. Okay, I will continue. Yeah. And sometimes we have to deal with the combined loading. And when we do a combined loading, you can see here, this one is the a combination between normal force, shear force, this one is normal force, internal normal force, internal shear force, and internal bending moment. Like that. Okay. And if we talk in the three-dimensional condition, this will be the complete condition. Okay, when we cut it, it will be the complete condition. So we will have actually this one is slightly this one is lacking of one thing. Okay, there is a possibility that we have a torsion as well there. So this is the complete one for two-dimensional case. We have shear force, we have normal force, we have bending moment, and we have torsion. Okay, this one is the complete one. Okay, but if we talk about the three-dimensional case, it's way more complicated because we have three forces in three directions, two shear forces, Vz and Vx, and one normal forces, Ny. Okay. Beside that, we have two bending moment, Mz and Mx. Okay, and one torsion, My. Okay. So in three-dimensional case, we have 6 components. But in two-dimensional case, we have 4 components. Okay. Sometimes not necessarily have to deal with those 4 components together in two-dimensional case. It depends on the condition. Okay. But you have to know that there is a possibility that those 4 components can come at the same time. Okay. And when we talk about the sign convention is about the positive sign. Okay. For normal force, as we know it, tension is positive. It's positive, and positive normal force is tension. So when we cut it, okay, when we cut, for example, we cut it here. Okay, the left cut, it will have a normal force like this, tension. Okay, internal normal force like this, tension. And the right cut, it will have an internal normal force like this, tension. Okay, then if we talk about the shear force, okay, the positive direction is supposed to be clockwise direction. So positive shear force is supposed to be like this. And if we do a cutting here, okay, the right side of the cut, okay, this one, will have internal force going downwards. And the left cut will have a internal shear force going upwards. Why it's like that? Because we have to make sure that the internal shear force is clockwise for the positive direction. Okay, when we do a section, always assume the positive direction first. Okay, as usual, always also assume the positive direction first. For moment, okay, it's quite simple as well. For moment, the positive direction is will make the beam smile. So the deflection of the beam will be smiling. The beam will be smiling. Okay, that's why the moment is like this, because that one will make the beam smile. Okay, yeah. And if we do a section here, the left side of the cut, it will be like this. The right side of the cut will be like this. That's the positive direction. Okay. So for positive moment, it will make the beam smiling. Now, the standard operating procedure in order to get the internal force is actually quite straightforward. Most of the time, you have to find the external support reaction. Then, after that, you do the imaginary section. Then, after that, you draw the free body diagram of one of the section. and then solve it using equilibrium equation. Okay, I think I will start with a simple example. Okay, on how to implement this particular standard operating procedure. For example, we have this beam. Okay, this beam, simple beam, and it has a pin joint on the left side, on the left edge, and roller on the right edge. And exactly in the middle, we give the beam with force of 10 kilonewton. Okay, and for example, I know that the beam length here is 2 meters. Okay. The first thing that the things that is asked in this particular problem is this one. I want to find out, okay, I want to find out the internal force at this particular location where x is equal to 0.5 meters. Okay, find internal force and moment at that particular location. Okay, so what we're supposed to do in this particular case? What we're supposed to do? Anyone can help me with this? Hello? Marcellus Mario.
Yes.
Okay. What's the first thing that we're supposed to do in order to do this, Mario? Based on the previous thing that we discussed.
Find the support reaction.
Find the support reaction. Find the support reaction. It means that we deal with, we try to deal with the whole free body diagram. Okay. So if we take a look at the whole free body diagram, it will be like this: 10 kilonewton. And at the left edge, what forces that we have there? Assume this one is A and this one is B.
AX, AY.
Okay, correct. This one will be AY, AX. And at the right edge,
BY.
BY only. Okay, we can solve this using using equilibrium equation, right? Okay, we can solve this using equilibrium equation. We have three equations. We have sigma fx equal to 0. By implementing sigma fx equal to 0, what we will get, Marcellus Mario?
AX is 0.
Ax equal to 0. Then after that, by implementing sigma moment at A equal to 0, what we will get here?
BY.
Yeah, By, correct. But would you mind to help me with the equation?
BY times 2.
Okay. By times 2 and
Minus 10 times
1. Yeah. Okay, equal to 0. So what we will get here is By. By there will be equal to what?
5.
Yeah, 5 kilonewton. And then using sigma Fy equal to 0, we will be able to find out Ay. Okay. It's quite simple. So Ay plus By, where By is known to have value of 5 kilonewton. So I will put it 5 kilonewton minus 10 kilonewton equal to 0. So Ay here we will have value L of Ly equal to 5 kilonewton. Okay, so now we solve OED of we solve the external forces OED, and then what is the next thing that we're supposed to do, Mario?
Make an imaginary cut.
Okay, we can do the imaginary cut. Where are we supposed to cut it? Where are we supposed to cut it?
At X.
At X, this point, okay? We do a cut there. Okay, and after we cut it, what we supposed to do?
Make a free body diagram of one of the cut.
Yes, correct. We can solve it by making a free body diagram of one of the cut. That's the point. One of the cut. So you can choose the left cut, or you can choose the right one. Okay. Either one is supposed to be okay. Okay. I will try first with the left one. Okay, with the left one, the cut supposed to be like this. Okay, AX is 0, so we only have AY, 5 kilonewton. And the distance here is supposed to be 0.5 meter. Then, what internal forces that we're supposed to put there, Mario?
Shear.
Shear force, okay, phi. And the positive direction, always assume with the positive direction, okay? Always assume the positive direction. For this case, this particular section, the positive direction is supposed to be going downwards or upwards. Remember here, for shear force, it's supposed to be clockwise. So this one is upwards or downwards?
Downwards.
Downwards, correct. Because it's supposed to be clockwise. Downwards, yes, will give you clockwise moment. Okay, so it's correct. It's downwards. What else that we have to put there, Mario? Hello, Mario.
Not sure.
Not sure. We can just draw everything. Okay. This one, we will have a normal force like this. We have a shear force, and normal force is supposed to be tension like this, right? And then moment, bending moment, the positive is supposed to be like this, right? To create the smiling beam. Okay. So I will add moment as well. Okay. Should be good enough, right, Mario? For torsion, because this one is a bending beam, beam under bending, it's not necessary for us to put the torsion there. Okay, the normal force as well here, using sigma fx equal to 0, we will be able to get that the normal force is equal to 0. So actually, later we can just delete the normal force. Okay, Mario. So basically, in this particular case, we only have a shear force and bending moment, right, Mario?
Yes.
Okay, now try to solve for the shear force, Mario. What we're supposed to do in order to find the shear force? Which equation that we're supposed to use?
Sigma moment.
Shear force, sigma moment. Are you sure?
Sigma Fy.
Yeah, sigma Fy. If you use sigma moment, okay, the moment there, we will have to include the moment there, right? I will just delete the normal force because it's 0. This one is moment, and this one is normal force equal to 0. Okay, so if we include, if we put the normal, if we use the sigma moment first, we will have to include the moment there, right? In order to solve for the shear force, we can use sigma Fy equal to 0. Okay, using sigma Fy equal to 0, what are the vertical forces that we have there, Mario?
5.
Hmm?
5 minus V.
So we have 5 kilonewton minus V equal to 0, right? So V will be equal to 5 kilonewton. So that is our shear force. Okay. Now let's deal with the sigma moment equal to 0. Where you want to put it, Mario? I mean, the location, the center of rotation. Where do you want to put the center of rotation, Mario, for the sigma moment?
At A.
At A, okay, correct. You can do it, or you can use the section location as well. You can do that, but you choose A, okay. And then what we have here,
V times 0.5.
correct? V times 0.5 meters
Minus M.
minus M equal to 0. Yep. And in this case, we know the value of V. V is 5 kilonewton. So 5 multiplied by 0.5 minus M equal to 0. So our moment will be 2.5. What is the unit here, Mario?
Kilonewton meter.
Or kilonewton meter. So this is it. We know the value of the normal force. Normal force is 0. We know the value of the moment, internal moment, 2.5 kilonewton meters. We know the value of the shear force, 5 kilonewton. Okay, Mario. Now, I want you to point one of your friend to help me with the next with the right section. I want to show you. I want to show it to you guys that solving the left section and the right section will give you the same result. Okay, Mario. Who wants you? Who do you want to point? Who do you want to point out? Would you mind to point out one of your friends to help me with this? Hello, Mario. Hello, Mario.
Lilo.
Lilo. Okay, Lilo.
Yes, sir.
Okay, Lilo. Mario wants you to help me to finish the right section. Just now we solved the left section, but now I want you to help me with the right section. This one. Okay, where are we supposed to start, Lilo?
We can like the three force, VM, moment, and normal force.
Okay, but before that, we have to draw the free body diagram, right?
Oh yeah.
Yeah, the section free body diagram. Don't forget about it. After you finish for the external forces, then the next thing that you're supposed to do is to draw the section free body diagram. Then after that, you can solve the internal force and moment using the equilibrium. Okay, let's try to. Wait a minute. I think this one is too cramped here. I will add another slide. Okay, let's draw it. Then we have 10 kilonewton, we have 5 kilonewton. So it's supposed to be like this, right? Okay, those are the external forces, right, Lilo?
Yes, sir.
So from here to here, it's 1 meter. From here to here, we have 0.5 meters. Okay. And what internal forces that we have there?
We have shear force, moment,
Shear
and
force, moment, and normal force. Okay.
normal.
Yeah, the same as before. But for shear force, as usual, I want you to always always start with the positive direction for the shear force. In this case, for the right section, the positive direction is downwards because it wants to create a clockwise moment. Okay, for this one, in order to create clockwise moment, the positive direction of V is supposed to be in which direction, upwards or downwards?
Upwards, sir.
So this one is V. And now about moment. How about moment? Will it be clockwise or counterclockwise for the positive direction? For moment, okay, in order to make sure in order to memorize it easily, the moment that will give a positive direction, the positive direction moment is the moment that will makes the beam smile. So the deflection of the beam will be smiling beam. Okay, so it's supposed to be clockwise or counterclockwise.
Clockwise, sir.
Clockwise. Are you sure clockwise? So like this.
I think that's counterclockwise.
Or clockwise. Yeah,
Clockwise.
clockwise, correct.
Yeah.
Okay, clockwise, correct. So this is the moment, clockwise. And then for the normal force, it's supposed to be always tension. So it's supposed to be going to the left or the right.
To the left, sir.
This one is the normal force. Okay, now try what we supposed to do next after we draw this particular figure diagram.
We use the equilibrium equations.
Okay, equilibrium equation. As usual, I will start with this one, sigma fx equal to 0. What we will get is normal force is equal to 0. Okay. This is for all of you guys. Okay. Most of the time when we deal with the bending beam under bending, okay, in our internal force and moment, normally we don't have to include this normal force. Why? Because most of the time it has no horizontal components of the forces, so it will be 0, like it or not. Okay, unless in the bending moment there is a horizontal force. If in the bending moment there is a horizontal force, then you have to add this one. Okay. And next, what we supposed to do then? Which one that we supposed to solve next?
We can do moment.
You can do moment. Sigma moment at which point?
At point B.
B. You mean
at
this one?
The far right.
If you do this, you haven't solved for phi yet, right?
Yeah.
Yeah. So you will not be able to find for the solution directly if you do it that way. Okay, Lilo?
Okay.
Okay. So if you want to use sigma moment in order for you to get the result directly, which center of rotation that we're supposed to use?
The far left.
Yes, correct. The far left at the section. Okay, at the section there, the moment due to phi will be 0, right?
Yeah.
Yeah.
Yes, sir.
So sigma moment at the section, okay, equal to 0. What we will have here?
The 10 kilonewton and 5 kilonewton.
10 kilonewton
and
multiplied by
moment.
what?
10 times 0.5 meter.
Okay. And then?
Plus minus 5 times 1.5.
Okay. And then?
and then plus moment.
Plus moment equal to 0. Okay. Then what we will get for the m there, for the moment there. This one will be 5. This one will be 7.5.
The moment will be 2.5.
2.5 kilonewton.
Yeah.
Okay, 2.5 kilonewton. And this one is 2.5 kilonewton. Sorry. Sigma moment at those location. Okay, 2.5. Correct, because this one is 7.5, this one is 5. So minus 2.5, 2.5 kilonewton positive, okay? So this one is the moment. And now, how about the internal shear force? How should we solve that?
We can use sigma Fy.
Yeah, correct. Sigma Fy equal to 0. What will you have there?
It's minus 10
Minus
plus 5
plus
plus
5
V
plus
equals to 0.
0. So V there will be
Equals to 5.
5 kilonewton. Oh, sorry, this one is supposed to be 5 kilonewton meter, okay?
Yeah.
So now let's try to compare. Okay, let's try to compare. Okay, if we use the right section, we have the moment 2.5 kilonewton meter and shear force 5 kilonewton. Okay, and if we use the left section, it's the same. The shear force is positive 5 kilonewton. The moment is positive 2.5 kilonewton meter. So whatever you do, whichever the section that you use, okay, left section or right section, the result is supposed to be the same, right? You can see it here. Okay. Is there any question about this? Okay, I will re-explain it in bahasa. Yeah, this is one of the simplest problem. Ini adalah permasalahan yang paling simpelnya. Ya. Contohnya, kita punya beam bending, beam mendapatkan beban bending yang dikasih beban pas 10 kN di tengah. Oke, beamnya panjangnya 2 meter. Yang ditanyakan adalah gaya dalam yang terjadi pada X itu lokasinya setengah meter dari ujung kiri. Nah, seperti yang sudah saya jelaskan sebelumnya, kita mulai dengan cara mencari besar gaya-gaya reaksi. Ya, jadi kita buat dulu diagram benda bebas secara keseluruhan untuk mencari gaya-gaya reaksi. Lalu kita bisa dapatkan gaya-gaya reaksinya. AX, AY, BY. Pakai sigma Fx, sigma moment, dan sigma Fy sama dengan 0. Gitu ya. Nah, setelah itu kita lakukan potongan. Kita potong di X. Nah, tadi bareng dengan Mario, itu saya coba selesaikan yang potongan kiri. Nah, untuk potongan kiri hasilnya seperti ini, diagram benda bebasnya seperti ini. Perlu diingat bahwa gaya dalam dan momen dalam yang kita harus gambarkan di sana itu adalah yang arahnya positif. V-nya arahnya ke bawah untuk menghasilkan momen clockwise, ya, supaya dia itu positifnya, arah positifnya, momennya counterclockwise, di sisi kanan itu counterclockwise, supaya bisa menghasilkan defleksi yang tersenyum. Normal force-nya tarik, selalu tarik ke arah kanan, seperti itu. Pakai sigma Fx sama dengan 0, sigma Fy sama dengan 0, sigma momen, kita bisa mendapatkan ketiga gaya dalam tersebut. Oke. Nah, kalau kita analisis yang potongan kanan juga, itu hasilnya akan sama aja. Harusnya memang hasilnya akan sama saja. Oke, ini adalah analisis kita tadi bareng Lido ya, untuk potongan yang kanan. Oke, gaya gesernya itu ke arah atas supaya bisa memberikan momen clockwise, momennya itu clockwise supaya bisa memberikan defleksi tersenyum, normal force-nya ke kiri, itu tarik arahnya. Oke, nah setelah kita gambarkan diagram berbebasnya, kita selesaikan pakai sigma fx sama dengan 0, sigma momen sama dengan 0, sigma fy sama dengan 0. Kita bisa dapatkan hasilnya harusnya sama persis. Di sini normal force-nya 0, momennya 2,5 kN positif, gesernya adalah 5 kN, dan bisa dilihat di situ ya, arahnya kebalikan, tapi sama-sama positif. Gaya gesernya arahnya ke atas untuk diagram badai bebas yang ini, dan yang ini, diagram badai bebas yang ini, gaya gesernya arahnya ke bawah, tapi sama-sama positif, karena itu adalah arah positifnya. Oke, kalau nanti disatukan, dia akan saling menghilangkan satu sama lain. Ingat ya, prinsip aksi reaksi. Momennya juga sama. Di sini momennya clockwise, 5 kN, 2,5 kN. Di sini momennya counterclockwise, 2,5 kN, saling menghilangkan. Seperti itu. Nah, satu lagi, untuk analisis beam yang mengalami bending, itu biasanya kita tidak perlu mencantumkan nomor dalam diagram badai bebas kita normal force, internal normal force di sana. Karena biasanya memang tidak ada. Oke, kecuali kalau misalkan memang dari diagram badai bebas gaya luarnya itu ada komponen gaya horizontal, baru kita cantumkan normal force di sana. Oke. Sampai di sini apakah ada pertanyaan? Tidak ada? Oke, untuk hari ini kita fokusnya hanya ke gaya dalam pada satu titik terlebih dahulu ya. Untuk hari Kamis minggu depan kita akan fokus untuk mencari gaya dan momen dalam. Diagram gaya dalam dan diagram momen dalam. Seperti itu ya. Nah, seperti yang saya sudah ungkapkan sebelumnya, kalau pada satu titik kita tinggal potong saja. Potong di titik yang dicari. Selesaikan section potongannya. Oke, selesaikan section potongannya. Nah, kemudian kalau misalkan kita ingin mencari tahu diagram gaya dalam dan diagram momen dalam, nah tujuannya buat apa? Diagram gaya dalam dan diagram momen dalam itu level selanjutnya. Tujuannya supaya kita tahu di semua titik pada struktur ini, oke, itu nilai dari gaya dalam dan juga nilai dari momen dalamnya berapa. Itu adalah diagram gaya dalam dan juga diagram momen dalam. Itu direpresentasikan dengan diagram gaya dalam dan juga diagram momen dalam. Seperti itu. Oke. Nah, tetapi untuk minggu ini kita belum sampai ke situ ya. Kita fokusnya hanya untuk yang pada satu titik terlebih dahulu. Pada satu titik terlebih dahulu. Ya. Nah, mungkin saya coba satu latihan soal lagi ya. Nanti sisanya kalian coba latihan sendiri dari PR yang akan saya berikan. Ini bisa dilihat di sini ya, ini nanti PR yang akan kalian harus kerjakan. Deadline-nya hari Kamis jam 10 pagi, Kamis minggu depan jam 10 pagi. Ya, ini mencari gaya dalam pada satu titik ya. Kalau yang ini lebih nomor satu itu lebih ke arah mencari gaya-gaya reaksi akibat gaya distribusi. Oke, lalu kemudian untuk nomor 2 ini diminta untuk mencari gaya dalam yang terjadi pada titik ini. L/4 dari support yang kiri. Oke, lalu yang gaya nomor 3 itu kalian diminta untuk mencari gaya dalam dan juga momen dalam, gaya normal dalam, gaya geser dalam, momen dalam di titik F dan juga di titik H. Oke. Lalu yang terakhir ini kalian diminta untuk mencari gaya dalam, gaya normal dalam, gaya geser dalam, dan juga momen dalam di titik D dan E. Seperti itu.
Excuse me, sir.
Yep.
It seems like your share screen is frozen.
Sorry. Wait a minute. Yep. So this is the homework that you have to do later. You can see here. The first homework is I ask you to solve for the external forces. Okay. Yeah, this is the external forces. If the external forces for you have to solve for the external forces at A and B due to the distributed force there. So number one is about distributed force. Number two, you are asked to find out about the shear force and internal force and internal moment at this particular location when the external forces is in the shape of a distributed force, like that. Okay. Then for number three, you are asked to find out on the internal force at F and H there. So you have to do section there. Okay. And number four, okay, you have to find out the internal force, internal shear force, internal normal force, internal shear force, and internal moment at E and D. Okay, so those are your homework. But now, for the last thing that I will discuss today, so I will use slightly more than, I will finish the class slightly more than 8 in the morning. Okay. This is the next thing that I want to discuss. Okay, how to find out the internal force at this particular location at the location C there. Okay, actually this one is very simple. Okay, I just want to discuss it a little. I want to discuss it faster. Okay, in order to find out the internal force and moment at C here, wait a minute. Okay, in order to find out the internal force at C there, okay, what you're supposed to do is just to do section there, and then draw the free body diagram of that particular section. Okay, why we don't have to solve for the external force here? Because as usual, when you do a section, we can solve for the left section or the right section. If you take a look at the left section, yes, we have to solve for all the external forces there. But sometimes we can choose for the other section. In this case, we can choose for the right section. The right section, all the knowns value are there. Okay, so we can just solve for that. If we draw for the right section, it will be like this. This is the distributed force. And that's it. We have to add the internal force as well at this section. Okay, so this is phi, this is moment. Okay, because there is no horizontal force, then this is it. This is our free body diagram that we have to solve. Okay, previously I already discussed about this. Okay, I will discuss it fast. Okay. Not previously, I have already discussed about this with you guys, but in last year, I already discussed about it. So if you want to know the detailed calculation, you can check my video last year. Okay, this is it. So when we want to solve for this one, okay, we can do the first thing, like what I taught you guys before. So solving for the external forces at A first, okay? Then after that, solve for the section here. But that one is not necessary. So the easier way to do it is to just solve for this particular section. You do the section, okay? You do the section, and then draw the free body diagram of that particular section directly like this, and solve for the internal moment, internal and internal force. Okay. If we do the section at this particular location, okay, this is what we will get. Sorry, the drawing there is a little bit complicated. So we have 600 Newton meters as the maximum force there, because remember here the maximum is 1,200 Newton per meter. So exactly in the middle here, the maximum distributed force supposed to be 600 Newton per meter. Okay. Then the maximum is 600 Newton per meter. We can get the and we have to draw for this all external forces and all internal forces and internal moment. And to solve for this, okay, we can draw the representation of the resultant of the distributed force. So we have 600 Newton meter, and then the length is 1.5 meters. So the total, okay, is 600 Newton per meter multiplied by 1.5 meters divided by 2. So the resultant will be 450 Newton there. Okay, and the location is supposed to be 1/3 from the left or 2/3 from the right. So the location is supposed to be 0.5 meters from the left. Okay, 0.5 meters from the left. Okay, then after that, you can delete the distributed force and just use the resultant force there for the calculation of the moment, internal shear force, like that. And we will be able to get all the things. So the internal shear force using sigma Fy equal to 0, we get the internal shear force is equal to 450 Newton. Using sigma moment equal to 0, we will get that the internal moment is equal to minus 225 Newton meters, like that. So I only explain about the concept on how to do things here. So in this case, after you draw the section free body diagram, then you can simplify the distributed load into the resultant of the distributed load. Okay, in order to solve for the problem. Okay, this is another exercise here. We are asked to find out the internal force, internal normal force, internal shear force, and internal bending moment at location B. So there you can solve for the left section or the right section. Okay, but first we have to solve for AX, AY, and the force at C there. Okay, it depends on which one that you want to solve, the left section or the right section. Okay, so if we take a look at this, okay, this is the free body diagram of the whole things to solve for the external forces. Okay, by using sigma Fx, sigma Fy, and sigma moment, we can solve for Ax, Ay, and Fcd. There. Okay, after you solve for those, then you can do the section. Okay, you can do the section. For example, here we use the left section. Okay, we use the left section. So if we know already the ax, ay, okay, then the left section will be like this. But remember, okay, you cannot use the simplified resultant force here for the internal force at point B, because it will be the wrong representation. Remember, you have to do the simplification of the distributed force for each free body diagram. So for example, I will try to solve the left section here. After finding out the ax and ay, then this will be my free body diagram. Ax and ay will be there. Okay, the distributed force will be there, and I do the section at point B. Okay, and I do the section at point B. So at point B there will be moment, normal force, and shear force. So all the internal force, I will put it there. Okay, all the internal force, I will put it there. Then we solve for this particular free body diagram. Yeah, after you draw this particular free body diagram, in order to solve this, yes, you can simplify it again, but the simplification is for each free body diagram. So you cannot just use the simplified version of the whole free body diagram and then cut it here and then use this as your new free body diagram. No, you cannot. So after you do the cutting from the original one, you draw again the whole free body diagram, the new free body diagram of the section, which included the distributed force. Then after that, you do the simplification. So for this one, the simplified version will be, the resultant will be here in the middle of the structure, of the section, like that. Okay. Okay. By using sigma fx, sigma fy, and sigma moment, we will be able to find these three values. Okay. Any question about this? Basically, what you need here is to practice more. Okay. So next week, I will start the class with the discussion on the homework. Okay, to ensure that you understand on how to solve our homework. Okay, on how to solve our homework. Okay, and then I will continue with the discussion on the internal force and internal moment diagram. Okay, so try it first based on our discussion today to calculate for the internal force here and here and here. Okay, and to calculate for the external force due to the distributed force here. Okay, as usual, at the start of our class on the on Thursday next week, I will try to discuss a little bit on our homework. Okay, then we will continue with the internal and moment diagram. Okay. Before I wrap up the class, anyone want to ask questions? Aurelia?
No questions, sir.
Okay, good. Muhammad Riki. Is it understood?
At the moment, sir.
Okay. So I think it's supposed to be okay, right? And try your best to finish the homework. And if you have any problem with the homework, we will discuss it at the beginning of our class next week. Okay. I think that's all. I think that's all for today. Okay. See you guys next week on Thursday. Please don't forget to check the EduNext for your homework. Okay, see you guys. Bye.
Thank you, sir.
Thank you,
Thank
sir.